Hello students, in this video we'll discuss conformal metrics to Euclidean space which are flat. Let's consider the family of metrics of conformal metrics So conformal metrics look like this, look like e to the 2f of xy, and then all the dx squared plus dy squared. So these are conformal to flat space, right? When is the resulting space flat? So when is the resulting space flat? i.e., when is R1, 2, 1, 2 equal to 0? Okay, so we need to compute this Riemann tensor, right? And so we need the Christoffel symbols for this thing over here, right? So what will the Christoffel symbols be? So let's recall what the nice formulas are. So what would gamma xxx be? So my gamma xxx is going to be the x derivative of the log, of the coefficient of x, right? Which is going to be the square root rather. So it's going to be just the log of the square root. So that's just going to be f of x, right? F of x, y, okay? Because remember the formulas are going to do the x derivative of the log of this thing. So what would my gamma of x, y is going to be the y derivative of the log of the square root of the x component, which is going to be just the f again, right? F of x, y. And then what will my gamma of x, y be? My gamma of x, y is going to be negative 1 over 2 e to the 2f. And now we're going to do the x derivative of e to the 2f, right? So what's this going to give us over here? Well, those are going to cancel out and you're just going to have an fx, right? So this is going to be negative 1 over 2 e to the 2f times 2 e to the 2f times f sub x, right? So everything cancels out, so just negative f sub x over here. Excellent. All right, and so by symmetry, what will we see over here? Well, by symmetry, we can see my gamma y is going to be the y derivative of f of xy. My gamma of y x is going to be the x derivative. So there's lots of symmetry involved in this, right? And finally, what's my gamma of y x? Negative 1 over 2 e to the 2f, the y derivative of e to the 2f, and by the same calculation, this is negative f sub y. So I have all my Christoffel symbols. Good. So now let's recall what the formula is for the Riemann-Christoffel tensor, right? So my let's do the simple one, the R1, 2, 1, 2, is going to be what? Is going to be, well, in general, let's do the general formula first and then plug in. That'll help us out. That'll help us see what's going on, right? So what's the general formula? My R, L, J, and P is the n derivative xn of gamma L, J, P minus the p derivative of gamma L, J, N plus gamma N, A, L, gamma A, J, P minus gamma P, A, L, gamma A, J, N, right? And so what will our formula be? So this is going to tell me that my R1, 2, 1, 2 is going to be what? My n is equal to 1, so it's going to be the x derivative of gamma x, and then my j and p are both y, so it's going to be a y. Then we have a minus y derivative of what? A y derivative, that's my p is y, right? Good. Of gamma what? Of gamma, my x is still x, and then I have a what? Then I have a j and an n. My j and n are going to be an x and a y. Okay, good. Then we have these mixed terms over here, so my mixed terms over here are going to be what? Gamma. The mixed terms over here, my n is equal to x, right? My n's the middle term, and that's going to be a 1. That's going to be an x. And then it's an x. I can do an x, a gamma x. And then my gamma what? My gamma a, and then jp. My j and p are yy. Plus gamma x, and then x again, because that's my n, x. And I can have a y, a gamma y, and then yy. And then minus gamma what? Na, so my n now is x. Let's see, I'm over here now. My p is y. X, and I can do an x, I can do a gamma x. And then I have a what? I have a j and an n. J and n are 1 and 2, so x and y. Minus gamma x, y, y, gamma y, and then xy, like that. So that's what my terms of my Christoffel tensor are. So let's compute them. All right, so it's my gamma 1, 2, 1, 2 is going to be the x derivative of x, y, y. So the x derivative of x, y, y is going to be negative f(x)(x), like that. Good. This term over here is the y derivative of x(xy), of x(xy). x(xy) is where? x(xy) is over here. x(xy) is the y derivative, so it's going to be negative fyy, like that. Then I have gamma xxx, that's going to be plus fx. Gamma xyy, xyy is going to be negative fx. Good. And then what? And then we have these terms over here. These terms over here, xxy. xxy is going to be fy, so that's going to be an fy. Then yyy is over here. That's going to be another fy times fy. Minus this term over here is going to be what? xxy. The xxy term is going to be fy. The xxy term over here is going to be fy again. And then finally this negative was negative xyy. xyy is going to be negative fx. That's a plus fx. And then this last term over here is xyy, which is negative fx. And then this term over here is the yyx. The yyx is going to be an fx. Now this term and this term cancel out, and this term and this term cancel out, so we just have what's left is the Laplacian. So now, that's great. And so now what we need to do is the following. And of course, that's good. And so now that's my that is my expression for this. And so what's my R1, 2, 1? Well, I have to take this and I have to hit it with a G11 R1 2, 1, 2 plus G12 R of 2, 2, 1, 2 like this. But it's a metric tensor. There's a conformal metric, so that term is gone. And so my G is just going to be what? My G11 is exactly just this e to the 2f, right? So this becomes a e to the 2f, like so. And then I have a negative Laplacian, right? Negative Laplacian of the function f over here. And so in particular, this says that the only time these metrics are flat is exactly when f is harmonic, right? So in other words, this metric over here, e to the 2f dx squared plus dy squared, is flat if and only if Laplacian of f is equal to 0 or f is harmonic. Okay? And so now what's the case? Well, I want to know, I'll address another question. So for which radial functions f does this work? So remember the Laplacian of f is frr plus 1 over r fr. But I'm looking for radial solutions to this. So if I set this equal to 0, what's this going to tell me? Well, if I integrate this, I can multiply this by r, and then r frr plus fr is equal to 0. That's a perfect derivative. So that says that r fr is a constant, which says that fr is a constant over r. And that tells me over here that if we were looking for the harmonic ones, the radial ones, that tells me that f of r is going to be what? Is going to be the log of r to the c plus another constant to d. And so if I plug that into here, we see that the only time, if I plug that, put the 2 in there, and that's going to basically just change the power of the r, right? And then the log and exponential will cancel out. So the only metrics, so if I look at metrics of this form, r to the c, right, times dx squared plus dy squared, we see that these are exactly the up to a constant, of course, another constant over here, d if you want, d1 for example. Those metrics over there are conformal to Euclidean space, just flat space, and these are also flat with respect to these metrics. So I need the Laplacian of f for these functions over here to be equal to 0 in order for the resulting space to be flat. So I can basically induce curvature by having functions which are not harmonic in the exponent of this conformal factor. Thank you very much.